Hello, then we continue this homework 2 with exercise 3. So here it comes. Exercise 3. First, a little information which we get in the text. Let omega be a sample space recall also that a probability function PR is a function defined for all events on omega that obeys the following axioms. Okay. The probability function PR must be such that every probability of any event A is bigger or equal 0. And II, the probability function of omega, is equal 1. And I for all disjoint events A and B, that is all events A and B such that A and B is equal is empty. Nothing common. So for all disjoint events A and B, that is all events A and B such that A and B is equal is empty, gives, then we have that the probability of A union B is equal probability of A plus probability of B. So how could we visualize this? We could have A there and B there, and then they have nothing common, but if we did like this, so here we have this joint, but now they are not disjoint, and this area or is A and B, not disjoint. But we are now working with disjoint, but yes, so okay. Now using I, and a couple of hints. We will show two results. One in exercise 3A and another in exercise 3B. Okay, so A. What we are going to do, show that the probability of B minus A is equal probability of B minus the probability of B and A. Okay, this can be easily visualized just looking at this draw actually, but now we are going to do this mathematically. So we get some information here. We use the hint that B is equal to B and A union B and A complement, like this. Let's visualize that. If we got A here and B here, we can see that if we let B and A be red, so this is B and A, and if we let B and A complement be green, so where is B and A complement? That's this one, and we can see that the green and the red together gives B. So that's the hint. And recall that B minus A is equal B and A complement. Let's visualize, and we can call this a star, and we can visualize it. So if I make A there and B here, so where is B and A complement? That's actually just the green part here. If this is A and this is B. And B minus A is just all in B, which not contains any from A. So then we understand the equality, hopefully. Then we have the probability for B is equal because of the hint, the probability of B and A union B and A complement. So this is using the hint. And this we can rewrite as the probability of B and A plus the probability of B and A complement. Why? Because B and A and B and A complement are disjoint. So this is because of I. Why is B and A complement disjoint? Let's look at it. If you see, remember, B and A is the red. If you see here. And B and A complement is green, but it's no overlap here. So these two events are disjoint. And then we're using the star. Which means that we can rewrite this last one as B minus A. So this is just using the star, and then we end with, and then we just rearrange. So the probability of B minus the probability of B and A is equal to the probability of B minus A. And we can change the equality here, so we can write this, because we normally read from left to right, it's better to write this as the probability of B minus A is equal to the probability of B minus the probability of B and A, like this. And what we were supposed to show. So this many can feel this a little hard because of a lot of notation, and actually it's very easy to see why the result is it's actually easy to visualize the result. But anyway, it's also possible to do this math to get to the result. But then we have to use this hint and this star, which we have used in this example. Then we got B. So here we are going to show that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. This is what we are going to show, but we get a hint. We will use the hint. A union B is equal to A minus B union B minus A union A and B. Let's visualize it, because else it's very hard to understand. A and B, and now let A minus B be red. So A minus B are this. It's all A except what's in contains B. So this is the red one. What is the green one? That's B minus A. And B minus A, it's all in B, what's not, which is not in A. So that's this one. This is the green. And then we have the last one. Let's make that a little colorful. And this is the part in the middle. So what we see that is that A minus B, B minus A and B is three disjoint events. They have nothing in common. And together they are A union B. Okay. This is not impossible. We got the probability of A union B is equal to the probability of A minus B union B minus A union A and B. This just using the hint. Just putting on the probability function on both sides. So, as we just saw, these three events inside the big parenthesis is disjoint. So, therefore, we can write this as the probability of A minus B plus the probability of B minus A plus the probability of A and B. And then we can write here A minus B and B minus A and B are all disjoint, and we use again property III, and property III is here. Probability of A or B or union B is equal to the probability of each one of the events in the union. So then we write this as probability of A union B equal, and this one I just use the result from exercise 3A, and there we found that this could be written as the probability of A minus the probability of A and B, and then plus, and the next one is the probability of B minus the probability of B and A, and in the end plus the probability of A and B. Then we see that, and this is then, so this last one is using exercise 3a, probability of a minus b is equal probability of a minus probability of a and b, and the probability of b minus a is the probability of b minus the probability of a and b. That was small, but we found it all in exercise 3a. So then we see that this one and this one cancel, and we got a union b is equal probability of a plus probability of b minus the probability of a and b. Okay, this is play with events, and now we have played exercise 3 finished. So then we can go to exercise 4. This was actually what we was asked to show them. Exercise 4. We define the conditional probability of a given b given that b is defined as following: the probability of a given b is equal the probability of a and b divided on the probability of b. And naturally, probability b has to be greater than 0. So let's start with a. Here we are asked to show that the probability of a and b is equal the probability of a given b times the probability of b, which is also equal to the probability of b given a times the probability of a. So let's see how we can do that. That's possible using the formula. For conditional probability twice, both for the probability of a given b and for the probability of b given a, we get, so let's do this. First time, the probability of a given b is, as you see above, the probability of a and b divided on the probability of b. And of course we now can multiply both sides with the probability of b. So doing that, we get that probability of a given b times the probability of b is equal to the probability of a and b. And if you now do almost the same here on the other side, we can now take, instead of calculating the probability of A given B, we can calculate the probability of B given A, which then gives the probability of B and A divided on the probability of A. But again, we can now multiply this time with the probability of A on both sides. And then we get this as the probability of B given A times the probability of A, which is equal to the probability of B and A. And what do we now see? We see that this and this is the same. And that means that, because you can always it's absolutely possible to, if you don't understand that, we could write this as A and B, that's actually the same. So just so no misunderstand here. So then it's very clear that this red, this here, is the same as this here. So we can conclude, and we see that the probability of A and B is equal to either the probability of A given B times the probability of B, which is this first one, or this is also equal to the probability of B given A times the probability of A. So that was A. Then we can go to B. Suppose this is an important exercise if you are going to understand the rest of it. So suppose that A1, A2, AK is such that AI and AK is empty for all j not equal I, and that A1 plus A2 plus ... plus AK is equal omega. So how can we visualize this? Because that's actually very important. We could have A1, A2, A3, and then we maybe have A4, A5, A6, and then we end with AK. So all little rectangle is one A1 or A2 or A3 and so on. And then we see that these events, A1, A2, and A3 is disjoint. And therefore A1 and A2 is empty. You can see it's no overlapping here, so that should be clear. Let's go on. So if AI and AJ is empty for all E not equal J, with other words, disjoint, which we just have mentioned, then also B and AI and B and AK has to be disjoint. Why is that? Let's visualize it, and let's do the draw again, and first make A1, A2, A3, and in the end AK, and let's put in a B here, and I could draw B wherever I want, but now I draw it, for example, here, B, and so now let's show this one, or visualize it. So example, B and A1 and B and A2 has to be disjoint. Is that true? And please now understand that B and A1, where is that? Let's mark that with red. B and A1, that's this one. That's between B and A1. What is B and A2? That is actually this one. Do the green and the red have anything common? No. Therefore, the red and the green are disjoint events, and the red is actually B and A1, and the green is actually B and A2. So that's why the text is written like that. So now we are so what we're going to do now is to show with the help above that the probability of B is equal the probability of B given A1 times the probability of A1 plus the probability of B given A2 times the probability of A2 plus plus the probability of B given AK times the probability of AK. So we are going to show this. Let's do it. We now know that the probability of B is equal the probability of B and A1 plus the probability of B and A2 plus the probability of B and and A3 plus plus the probability of B and AK. Why is that true? The probability of B, let's look at the draw. The probability of B is this this black here, this one, and we can say that B is the same as the red one, which is B and A1, plus the green one, which is B and A2, and then go on with B and A3, B and A4, until B and AK. That's correct. that's for sure. So then we know this, and we can continue with rewriting this from exercise 4a. We got probability of B is equal to this first one, can be written as the probability of B given A1 times the probability of A1 plus this one can be written as the probability of B given A2 times the probability of A2 plus and then this one can be written as probability of B given A3 times probability of A3 plus dot 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 plus the probability of B given AK times the probability of AK. So this is from exercise 4a. So then from exercise 4a we know that this first one can be written as this. Just look at exercise 4a and so on. And this was actually what we were going to show, and we can write this more beautiful by using a summation sign. I equal 1 to k, and the probability of B given AI times the probability of AI. Okay, and then we go for C. Now it's get a little more easy. We deduce Bayes, the well-known Bayes theorem, Bayes theorem. Probability of A given B is equal the probability of B given A times the probability of A divided on the probability of B. This is Bayes theorem. We deduce this theorem from the formula for conditional probability. So if that's possible, we have to start with the conditional probability, and we see what we are going to get. So I start with the conditional probability. The probability of A given B is given by a formula which is the probability of A and B divided on the probability of B. But the probability of A and B we know can be written as, for example, the probability of B given A times the probability of A divided on probability of B. So yes, so this should be quite clear from the exercises we did earlier in 4a and 4b. especially for A. Okay, D. Now we get a little information first here. A1, comma A2, comma dot dot dot, comma AK are sets such that AI and AJ is empty for all J not equal I, like above. And that A1 union A2 union dot 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 union AK minus 1 union AK is equal omega. So if we sum over all these A's, we got the total sample space. And now we are going to show that the probability of AI given B is equal to the probability of B given AI times the probability of AI divided on the sum J equal 1 to K probability of B given AJ times the probability of AJ. Okay. Then we have to do it. And this we will do just using the results from exercise 4b, where we found that the probability of B is equal the sum J equal 1 to K, probability of B given AJ times the probability of AJ. And exercise 4C, where we have that the probability of A given B is equal the probability of B given A times the probability of A divided on the probability of B. So this is what we're going to use to show the result above. Because these two exercises, or these two formulas written here now, gives the probability of AI given B is equal the probability of AI and B divided on the probability of B. But as we know, probability of B. This is just the Bayes theorem. So we can write this as the probability of B given AI times the probability of AI divided on the probability of B, but the probability of B, that's actually the sum j equal 1 to k. The probability of AJ given, the probability of B given AJ times the probability of AJ. For any I. I could show this for especially A2, but we have done the exercise now, but for example, let's take let I be 2. Let I equal 2. Then we get the probability of A2 given B is equal to the probability of A2 and B divided on the probability of B. But we know that this first one can be written as probability of B given A2 times the probability of A2 divided on the probability of B, which is, we could write just the sum j equal 1 to k probability of B given AJ times the probability of AJ, or we can write it totally out like this, which maybe give more information and understanding. So we rewrite the sum as the probability of B given A1 times the probability of A1 plus the probability of B given A2 times the probability of B given, probability of A2, 1 there and 2 here, plus plus the probability of B given AK times the probability of A. Okay. Yes. Then we are going to take E, and that's actually a little practical and a bit more fun, I believe. I will just check over a couple of things here now. Okay. So then it's E. And here, now we're going to see if these COVID-19 tests are good or not, or just try to understand a little about testing. So let's define S. We can call it sick, but we don't. Define TS, which say test says infected or sick. And we can say that TS with a bar over is that the test says not infected or sick. And S is equal infected or sick. Many don't get sick then, so. And not sick, not infected, S bar, so that's not infected. We have to denote these events. You could use other notation if you want, but now we use this one. So then we got from the text that the probability of test says infected given that you are infected, that's 0.95. So it's pretty sure that the test gives the right answer if you are sick. But actually, the test tells you that you are sick, even if you not are, with a pretty high probability, 0.1. So if you are not sick, the test will say that you are sick in 10%. But what is the chance that you are sick in this society? It stands that it's 10 out of, or infected then. It says that it's 10 out of 100,000, which is equal to 0.0001. And the probability of being not sick or infected, that's of course then 99,990 divided on 100,000, which is equal 0.9999. So, what are we asked to find? We are asked to find the probability of being infected or sick given that the test says you are sick. And what is the result here? Everybody almost believes that this will be a very high number. The problem here is that it's pretty few people being infected and very many not being infected, and also a very big chance of, and also 10% of all the tested people which are not infected will have a positive test. And this will make it hard to get good results, if you can say it like that, when calculating this probability of being sick given that the test says you are sick. It will be much lower than you believe. And think about it by looking at the numbers here. Let's now do it. So the formula, this is Bayes' theorem, so we get the probability of test says sick given that you are sick times the probability of being sick or infected divided on the probability that the test says sick. So then we put in the numbers. We see that the first one is 0.95. We see that the next one is 0.0001. And the last one, probability that the test says sick, then we have to use the law of total probability, which says that either you are not you are sick, 0.001 times the test says you are sick, if you are sick, or you are not sick times the probability of the test says sick, which is 0.1. And do we calculate this, we get 0.00094, which is almost 0.1 or 0.094%. Is the probability that you are sick given that the test says so. So actually we don't know very much of the person which have a positive test. It's a very big chance, very, very big chance that he is not infected at all. So then we see that it is a very, very little probability for that given that the test says you are sick, that you really are sick. That was bad English, I think. So maybe it's just wasted money to test a random person but of course if the person has symptoms it will be otherwise. So then that was exercises 3 and 4, and we will make a last video with exercises 5 and 6. Maybe going a little faster than this one. Okay, have a nice evening, morning, lunch, run, strange. Okay, hey.